Hello everyone. There have been quite a few people on YouTube, and no doubt also in many other places as well, who've devoted quite a bit of their time and quite a bit of their attention to the alleged philosophical implications of quantum mechanics. Indeed, if we're going to look at a choice selection of a few YouTube channels, we'll see that there are in fact fairly prominent channels with reasonably high subscriber counts that have been, if not entirely devoted to exploring some alleged philosophical implication of quantum theory or arguing for some said implication or interpretation, have at least produced a substantial number of videos devoted to that project. And so arguing for that has become a substantial part of the YouTube output of quite a few people. I have in mind, of course, people like Inspiring Philosophy, Johann Ratz, and a few others. I know for a fact that there are at least some people who are subscribed to me who are aware of these YouTube personalities. So I trust that those listening will know what I'm talking about. If not, I'll provide links in the description of this video to paradigmatic selections of the sorts of channels and the sorts of people who push the sort of argument that I have in mind. Now, in particular, as far as the philosophical implications, alleged or otherwise, of quantum mechanics go, there is one in particular that I want to focus on. And this is the claim that quantum mechanics, and in particular the results of the double slit experiment, in conjunction with various other lesser known experiments which really more or less derive from the double slit experiment, as well as a few other theoretical discoveries of theorems within the quantum mechanical formalism, things like the kochen-specker theorem and so forth. It has been claimed that the conjunction of all of these discoveries within quantum mechanics prove idealism. And what I'd like to do is discuss some of the arguments to that effect. And then once I've done so, to make a few elementary points about the philosophy of science and the nature of scientific theories. And having done that, I will then pose what I think is an enormously important objection to all of these claims, and I will do so without even having discussed physics at all. The point will be that there's a certain basic logical and philosophical problem at the very core of quantum mechanical arguments in favor of idealism. And to get at that assumption, one need not even discuss physics. This will come out, as I said, once I make a few methodological points about the philosophy of science. Now, although there are other people whom I can focus on in discussing these sorts of quantum mechanical arguments for idealism, I'm going to focus on Inspiring Philosophy simply because his videos are really snazzy and they're fairly comprehensive. And although other channels on YouTube, like Johann Ratz's channel, have also made arguments to the same effect as those of Inspiring Philosophy, although they might not be precisely the same, and although they might not make precisely the same claims, it nevertheless is the case that these others more or less agree with what has been claimed by Inspiring Philosophy, may even accept the specific arguments that he puts forward, and so on. And in fact, even if one can think of quantum mechanical arguments which he does not point to, the methodological considerations that I'm going to bring up here will reduce any such point to irrelevancy, essentially. I hope to make that clear in a moment. So before I get to that, let me go through a number of Inspiring Philosophy's claims. So, I'm really going to focus in this discussion on three videos of his. One is the sort of general video that he made called Quantum Mechanics Debunks Materialism, which is as I said, more general. He goes through a few discoveries in physics and argues that they point toward an idealistic metaphysical conclusion. The other video pertains to the measurement problem, and then he has another third video devoted specifically to one experiment in particular, which is called the delayed choice quantum eraser experiment, which I'll discuss in a moment here. Now, before I begin, though, let me, just for the sake of clarity, set down a definition of exactly what I mean by idealism, and I hope that this point will be uncontroversial. By idealism, I mean the metaphysical or ontological, if you like, thesis that reality is mind-dependent. That is, that there is no objective mind-independent reality as such. This is usually expressed in Bishop George Berkeley's famous dictum that to be is to be perceived. Now, I'm not saying that every idealist is necessarily a Berkeleyan, but that sort of general tenor is nevertheless present in all idealistic thought. So by idealism, I just mean the claim, the metaphysical claim, that reality is ultimately mind-dependent. That it is the presence of mind which makes the objects that we take to be real, and that those objects really are not independent of our minds in the way that our preconsidered intuitions may perhaps lead us to think. So, what does inspiring philosophy and those who follow him, or agree with him at least, claim quantum mechanics has to say about idealism? And why do these people claim that quantum mechanics proves that idealism is true? Well, for starters, the famous double-slit experiment in quantum mechanics, in which electrons were fired at a plate containing two slits, and then allowed to pass through those slits and make contact with a screen behind the slits, at which point the pattern that the electrons produced on the screen was observed. It was a very famous experiment in quantum mechanics. It essentially opened up and led to the creation of the field, and it's produced many mind-boggling and baffling puzzles ever since that people have been arguing about. The experiment is as follows. There is a plate with two slits, a screen behind the plate, and an apparatus that fires electrons at the plate. The electrons, as I said, pass through the slits, and they make contact with the plate. Now, it was believed, when this experiment was initially done, that electrons, being electrons, were, of course, particles. And so it was thought that if one were to fire a series of electrons at these plates, they would produce a clump pattern on the slit. That is, behind the area where one slit was present, you would see a sort of clumping distribution of electrons, indicating that they had passed through that particular slit, and the same would also be true of the other slit. And so you'd have these two clumps of electrons having made contact with the screen behind the plate with the two slits. However, it was found, to the bafflement and confusion of the physicists at the time, that once these electrons were fired at this plate, they in fact did not produce this expected clump pattern. Instead, what happened is that they produced an interference pattern that was like what one would expect if one had been blasting waves of some sort at the slits rather than particles. So there was this wave-like interference pattern that was produced. See, if you actually fire waves at this plate with these two slits, what happens is that these waves will collide with one another, they will interfere, and then they will produce an interference pattern, and that interference pattern will become evident on the screen behind the slit. And as I said, it was found that once electrons were fired at this plate, you had a wave-like interference pattern instead of the expected particulate clump pattern. Now, initially, physicists supposed that perhaps this bizarre result occurred because electrons were colliding with one another and hence interfering with one another, thus leading to this bizarre sort of wave pattern. So they decided to alter the experiment by taking special care to only fire one electron at the plate at a time. But despite having done this, they still saw the same wave-like interference pattern. So they decided that they would place a measuring device at the slit to see what was going on with the electrons as they passed through those slits. And it was found, to their further surprise and bafflement, that upon placing a measuring device by the plate near the slits so that the electrons could be observed as they passed through them, the pattern which the electrons then produced upon the sheet behind the plate became the clump pattern that one would associate with particles. Something about the presence of a measuring device caused the electrons to go from behaving like waves to behaving like particles. This is very odd. It's a very odd result. There's something about it, or at least it seemed to be the case, that there's something about the act of measuring, the act of actually observing, and so on, of actually attempting to determine what the electron is doing at some particular time, that actually winds up altering the behavior of the electron. This is known in physics as the measurement problem. And this result, as I said, essentially produced the field of quantum mechanics. Now, Niels Bohr and Werner Heisenberg, the two founders of the field, produced how should I say this? Well, they essentially created mathematics, or made use of mathematics rather, that attempted to describe the behavior of electrons or particles statistically. And what they said was that prior to observation, particles exist in a joint superposition state, so that the precise location of a particle cannot be ascertained. All that can be said is that there is a given probability distribution associated with a given area, and that based on that probability distribution, one has a certain given percentage chance of finding the electron in some particular area. So this essentially is what's known as the Heisenberg uncertainty principle, that one cannot ascertain certain information, in particular either the precise location or the precise velocity of a particle. If one can ascertain the one cannot ascertain precisely the other. For reasons that I hope will be made clear later on in this video, it would have been much better if Heisenberg had chosen to call his principle something like the principle of imprecision. But essentially what happened is that the mathematics of quantum mechanics had described particles prior to observation as existing in this state of superposition as a mathematical distribution of probabilities. Then, upon observation, or upon placing a measuring device in some given area, around the particle, that observes it and records what it does, the particle suddenly goes from existing in a state of probabilistic distribution to actually converging on some particular point. This is called wave function collapse. So the particle goes from existing in this joint superposition state to actually then occupying a definite point in space, a definite area, having a definite location, a definitely ascertained location. And there's something about the act of observation that seems to do this. Or at least That's what Heisenberg and Bohr claimed. So, what inspiring philosophy and those like him do is they point to this. They say, prior to observation, particles exist in this joint superposition state. Something about the act of observation collapses the wave function, causes the particle to converge onto a particular location. And they say that what enables this to happen is the presence of a conscious observer. That is to say, consciousness itself somehow interacts with the superposition kind of probabilistic distribution, or the particle, or quote-unquote particle, when it's in its wavy probabilistic distribution state, and then causes it to converge on a definite location. Something about the interaction of consciousness with that system causes wave function collapse. Now, he claims this in response to arguments made by some people who say that it is not the presence of a conscious observer that causes wave function collapse, but simply interaction with the physical measuring apparatus. Now, inspiring philosophy's response to this point is to point to an argument made by the mathematician John von Neumann when he set about doing his work in formalizing quantum mechanics and really giving kind of formal mathematical description of its entire theoretical apparatus and laying down its mathematical foundations and so forth. What von Neumann said was that in order for it to be the case that the presence of a measurement apparatus collapses the wave function and causes the particle to converge to a definite location, you first have to be able to explain what it is that does that very thing for the particles of which the measurement apparatus itself is composed. Because those particles themselves obey quantum laws. And so something has to be there to collapse the wave function for the particles comprising the measurement apparatus. And then something has to be there to collapse the wave function for comprising the particles of that measurement apparatus. And so on and so forth in an infinite chain. And what von Neumann hypothesized, or what he claimed, is that in order to terminate this infinite regress, one has to postulate something outside of this material chain, something outside of purely material reality, which is able to collapse this whole chain of wave functions and actually produce a definite localization of objects within reality. And von Neumann said that this was a conscious observer. So this is the sort of von Neumann chain argument. Another point that inspiring philosophy brings up quite a lot is something called the kochen-specker theorem. And I'll provide a link to an excellent article in the Stanford Encyclopedia of Philosophy about the kochen-specker theorem, which provides a proof of the theorem and all sorts of things like that that anyone might be interested in. It's worth having a look. But to give a very quick, brief explanation of what the theorem states, it says that the conjunction of value definiteness and non-contextuality contradicts the quantum mechanical formalism. That is, from the conjunction of the claim of value definiteness and non-contextuality, one can derive mathematically a contradiction with the quantum mechanical formalism. And so one can't accept both that conjunction and the quantum mechanical formalism. Alright, now to explain what I mean by value definiteness and non-contextuality. Value definiteness is just the idea that the elements of a quantum system all have definite values at each point in time. They all have definitely determined values at every point. So, for example, every particle in a quantum mechanical system would have a definite location, a definite velocity, a definite spin, and so forth. All of its properties would have definite values assigned to it. That's what value definiteness is. Non-contextuality is just the claim that the environment in which some quantum system is present, including the presence of a measurement apparatus or an observer, do not themselves affect the features of that quantum system. So it's the claim that what goes on in a quantum system can be separated from the observational context in which it's present. It's not dependent on observational context. So it turns out that the conjunction of these two assumptions contradicts the axioms of the quantum mechanical formalism at some level. That is the kochen-specker theorem. But so that means that you have to reject the conjunction of value definiteness and non-contextuality. Now, you can believe in one or the other, but you can't believe them both. This is why I emphasize the conjunction. So what physicists typically do is they reject the non-contextuality assumption. So that means now that the presence of either a measurement apparatus or a conscious observer actually affects the state of the quantum system. And what inspiring philosophy wants to suggest with this argument is that the effect which the conscious observer has on the quantum system is that he produces, by dint of his consciousness and by dint of the sort of free choice about what to observe that the conscious observer makes, is that he collapses the wave function. That's precisely the change that he initiates, that the particles in the quantum system go from that mathematical superposition state when they are unobserved to having definite location and definite values for its other parameters once they have been observed. So that's another one of his arguments. Now, Albert Einstein, of course, quite famously, was bothered by quantum mechanics and its apparently bizarre implications. And he proposed a rather famous thought experiment along with two other physicists, Podolsky and Rosen, in which he said that one could take two particles and entangle them in such a way. And entanglement is really just some sort of mysterious relation between two particles which physicists don't quite understand the nature of yet, which leads them to have complementary properties, complementary quantum mechanical properties. If one entangled particle in a pair of entangled particles has some particular value for its spin, the other will have the corresponding value for its spin, and so on. So there's this kind of complementarity there. So what Einstein said is that if you entangle two particles, and then you split them apart and bring them to opposite ends of the universe, to say that observation collapses the wave function and thereby grants to the particle being observed all of its quantum mechanical properties, you would have to say that instantaneously, upon the very moment that one of the two entangled particles is observed, its wave function collapses, it gets the properties that it inherits, and then instantaneously information travels to the other end of the universe and imbues the other entangled particle with the corresponding properties, the complementary properties. And of course that can't happen because then information would have to travel faster than light, and that's just nonsense. That's just ridiculous. So what Einstein said then is that there has to be some sort of local hidden variable, some aspect of the system of which we are ignorant, which explains how this process goes on. And essentially, as is well known in physics, I suppose, John Bell proposed an inequality and then also a famous thought experiment which was finally carried out experimentally in the 1980s, and his inequality was violated, which showed that indeed the kind of spooky action at a distance that Einstein insisted could happen did in fact happen. And so what this means is that realistic theories of quantum mechanics, that is, non-idealistic theories, theories in which or interpretations of quantum mechanics in which the conscious observer or consciousness itself is not said to have a role in collapsing the wave function, cannot be local. They cannot make the assumption that these hidden variables are local. And so the only recourse then is for non-local hidden variable theories. That the only realistic interpretations of quantum mechanics can be non-local theories. That's what Bell's theorem said. Now he makes a few other arguments. For example, in the video called "Quantum Mechanics Debunks Materialism," he makes a very passing reference to the Leggett-Garg inequality, which dealt with non-local hidden variable theories, and claims, again, in a passing, oblique sort of way, that there was a paper written by Anton Zeilinger and a number of other physicists which allegedly debunked all of these non-local hidden variable theories. Now, he doesn't go into detail about exactly what was done, and that's crucial when I get to the point where I'm formulating my response to all this stuff. I strongly suspect that he only spent a few seconds on this point for a reason. He either didn't actually read what it said in the paper he cited, or he hoped that his viewers wouldn't do so. I'll explain why in a minute. So there's that argument. And then he also refers to an experiment called the delayed choice quantum eraser experiment. Now, in simple terms, this experiment is a modified version of the original double slit experiment. Only here, what happens is that electrons are fired, allowed to pass through the slits on the plate, and it is only after they pass through those slits, but before they collide with the plate, that they are observed. And it is found that even though the electrons, when initially fired and when they go through the slit, behave in a wave-like manner, that is, as a particle as a sort of mathematical distribution of superpositions and probabilities, upon being observed, they instantly begin to behave like particles. He does, in his video about the delayed choice quantum eraser experiment, give an explanation of a more detailed version of the experiment in which he presents a diagram. You can watch his video and have a look at the diagram for yourself, but on the diagram there are two slits A and B from which photons can be fired and from which they are fired at random, and then 5 detectors labeled D0, D1, D2, D3, and D4 placed at various locations. And for 2 of the detectors, I believe D2 and D4, it is possible for a photon to reach those detectors regardless of whether it was originally fired from location A through slit A or through slit B. And what he points out is that the experiment revealed that if for all photons which collide with either detector D2 or D4, where it's ambiguous whether the photon was originally fired through slit A or slit B, there is a wave-like interference pattern produced. But on detectors D1 and D3, where there is a clear path information, and where it is obvious that the photon in question either came from slit A or slit B, because the only way that it could have arrived at one or the other of the 2 detectors would be if it was fired from definitely one particular slit or the other. In that case, it always produces the sort of clump pattern that one would expect from particles. Even more than this, upon the determination of the path information, that is, in the case where we know for sure what the path information was, and we see the clump pattern, the experiment appears to load up a back history for for the photon as it had traveled to that detector, making it so that it had been acting as a particle all along. And he says this is very odd because, upon initially being fired and upon, before it's observed, the photon exists in a superposition of states and does not behave as a particle. But upon our being able to ascertain the precise path information of the particle, in the case where it collides either with detector 3 or detector 1, it begins to act as a particle, and the prior behavior of the particle upon reaching either of those detectors also becomes particulate. And again, you can see this clearly laid out in the diagram if you just sort of follow the paths. So what he says is that, again, it is our knowledge of the path information, and hence our observations of these particles, of these photons, that determine whether they behave like spread out waves in a mathematical superposition, or whether they behave like particles. And so it is the active observation itself which gives the definite, precisely located particulate quality of the photon to the photon. And this, he says, also is an argument in favor of idealism. All right, now I think I've gone through all of the major arguments at this point, and I think I've stated them more or less clearly and fairly. So what I'm going to do now is I'm going to go through a number of important but basic points in the philosophy of science, some methodological points. And once I've gone through those, I'm going to use that to segue into saying that there is, within the Copenhagen interpretation of quantum mechanics that those who believe that quantum mechanics proves idealism favor, a philosophical assumption which is not justified by quantum mechanics itself, and which in fact cannot ever, even in principle, be justified purely by quantum mechanics itself. And that merely pointing this out is enough to undercut the entire argument and destroy the claim that quantum mechanics proves idealism, even if the assumptions in question happen to be true. All right, so the first point that I want to make is just the basic point in philosophy of science that theory is underdetermined by evidence. All this really means is that for any given collection of observation statements that a scientific theory is constructed to account for, it is always possible to construct more than one scientific theory which accounts equally well for all of the observation statements in the set. For any set of observations, you can construct at least two, and in fact probably an infinite number of theories, which make different starting assumptions, but which account for all of the facts that you'd like to account for. And if you expand the set of observation statements, you may rule out some of the theories that previously couldn't be ruled out, but you'd never be able to narrow it down just to one theory. So theory is always underdetermined by evidence. No set of observation statements, however large, can ever narrow things down to the point where just one scientific theory and only one scientific theory can account for the evidence in question. Now, the second point I want to make ties in with the first point. And that is that because in science theory is underdetermined by evidence, the only way in which one can distinguish between alternative scientific theories, which all equally account for the same set of observation statements, is by the initial metaphysical assumptions made by those theories. Now, they don't always have to be metaphysical assumptions, but generally they are, and they are assumptions of some sort. The theories can only be distinguished by reference to those things. So, to give an example, take Ptolemaic astronomy. Now, Ptolemaic astronomy began with the assumption that the Earth was in the center of the solar system. And then Ptolemy gathered a series of astronomical observations, and he played with geometry until he was able to contrive a geometrical system with epicycles and deference and so forth that was eventually able to account for those observations. Okay, so it isn't, for example, that Ptolemaic astronomy proved that the Earth was at the center of the solar system. It's just that given the assumption that the Earth is at the center of the solar system, it was able to generate a mathematical apparatus which could account for the observations that he had access to in a way that was consistent with the assumption that the Earth was at the center of the solar system. So, for example, if you were to go to a Ptolemaic astronomer and ask him, how do you know that the Earth is at the center of the solar system, he wouldn't be able to say to you that, I know this because that's what the geometry shows, that's what the math shows. That would be completely wrong. Rather, the assumption that the Earth is at the center of the solar system is made, and then you play with math until you arrive at something which can enable you to construct a theoretical model which assumes that the Earth is at the center of the solar system and is able to account for the observations that we have present. Now, Ptolemaic astronomy then, as such, for someone who really understands how scientific theories work, would then really have no ontological commitments with respect to the claim that the Earth is at the center of the solar system. It's just a postulate of the theory. It doesn't have to claim that that's really true. And this leads to an important point. Scientific theories can make background assumptions which are false, but if one can go from those false assumptions to the construction of a theoretical model which nevertheless is able to account for the observations that one has to account for, that scientific theory is adequate. Even though its assumptions may be true or false or what have you, there's no ontological commitment to the truth of those assumptions. So, even though Ptolemaic astronomy was wrong to assume that the Earth is at the center of the solar system, it nevertheless was able to make accurate predictions with respect to the observations that were available at the time. And you can make similar points about any scientific theory. The point of science is that because we do not always have access to the deep underlying metaphysical causes or principles of the objects of reality, we must, in the construction of our scientific theories, often settle merely for preserving the phenomena. That is, anything that accounts for observations is good enough, and if the theory postulates certain entities as part of its basic assumptions, it's not necessarily to be assumed that those entities actually exist. Okay? A theory can postulate entities that don't exist and yet account for observations accurately. So that's an important point to make. And what all of that means is that with any scientific theory whatsoever, one must come at the theory with a framework of philosophical and metaphysical background assumptions which frame how one is to interpret the observations that one has to collate together and explain within the scientific theory that one's proposing. So, every scientific theory has certain background metaphysical assumptions, and those metaphysical assumptions describe and set limits to how one can interpret and understand the data that one gathers from observations. Those data, together with those metaphysical assumptions, give you limits as to, or parameters, as to what your theoretical models can look like in your scientific theories. Okay? And scientific theories are always going to be limited by those background assumptions. Now, most physicists and most scientists in general really make certain philosophical and metaphysical assumptions unconsciously or without realizing it. And I think that this was the case with Heisenberg and Bohr. They make certain assumptions about metaphysics, don't realize that they're doing it, and they thereby unwittingly set up parameters to the interpretation of their physical data that constrain what their theories can look like. And as often happens, they're not going to be very attentive to those background philosophical assumptions that they're making. And when they're not attentive to these things, they will often make the mistake of claiming that their scientific work refutes or at least or argues for or poses objections against some metaphysical or ontological thesis or other. And this is a mistake. I'm going to link to a number of posts from Edward Feser's blog in which he discusses an issue related to this. Now, he doesn't talk about quantum mechanics and idealism in these posts. He talks about quantum mechanics and the claim that it has allegedly refuted the principle of causality or the principle of sufficient reason. But the points that he makes in these posts can, mutatis mutandis, be applied to the discussion of what I'm talking about here. And I'd just like to read a brief selection from one of those posts. It's a post on causality that really highlights the central issue. Now, Feser, for those of you who don't know, is a Catholic philosopher, and he believes in Aristotelian Thomistic metaphysics. Now, you don't have to follow him on that point to see the truth of what he's saying. That is, you don't have to accept scholastic philosophy or scholastic metaphysics to really understand the point that he's making. But here's the bit from his blog that I'd like to read to you. He says, quote, "It's never really the empirical or scientific details that are doing the work in objections to scholastic metaphysics like the one at issue," mainly the issue that quantum mechanics refutes causality. "What's really doing the work is a ton of philosophical baggage that the critics unreflectively bring to bear on the subject. The assumptions they read into the physics and then read back out again, thinking they've raised a scientific objection, when what they've really done is raised an objection a question-begging philosophical objection disguised as a scientific objection." That's exactly right. So having made this point, that all scientific theories can only be and must necessarily be formulated within the framework of certain metaphysical assumptions, whether implicit or explicit, what does this have to do with quantum mechanics? Well, Bohr and Heisenberg made two assumptions about how to interpret quantum theory and the results of things like the double slit experiment. And metaphysically speaking, these two assumptions are absolute whoppers. And not only are they absolute whoppers, but it is completely impossible, even in principle, to justify them using physics alone. And the assumptions are as follows. Assumption number one is that the mathematical description of particles as existing in a superposition probability distribution prior to observation actually refers to a real phenomenon. There is no justification whatsoever within quantum mechanics for that claim. None. There is no reason to take the mathematical apparatus that Heisenberg and Bohr devised and claim that the structures proposed by that apparatus refer to anything in reality. That is just something that they assumed. Now, remember the earlier point that I made, that scientific theories need not always make realistic initial assumptions. The only things that they need to do is to generate correct predictions. Now, the mathematical description of unobserved objects existing in a joint superposition enables one to correctly predict the behavior of objects in all sorts of quantum mechanical experiments. But that does not imply that the mathematical description of objects in a statistical superposition, once they are unobserved, refers to the actual state of those objects when they in fact are unobserved. This is a simple reification error. They're taking a mathematical construct which was designed simply to produce a useful model which can generate accurate predictions, and they're imputing ontological status to it in a way that is completely unjustified. And it is completely unjustified because quantum mechanics itself cannot provide the justification for doing this. That assumption, in fact, is one of the background philosophical assumptions of the Copenhagen interpretation of quantum mechanics, which enables that interpretation to even be able to make sense out of any experimental data. That assumption is one of the filters through which the experimental data of quantum mechanics is passed through under the Copenhagen interpretation. It is through that assumption, and another one that I'll get to in a minute, that experimental data in quantum mechanics under the Copenhagen interpretation is understood. Okay? So there's absolutely no reason to grant real ontological status to this mathematical notion of objects existing in a superposition. None. And if you want to insist that this is in fact the way that objects behave when they are unobserved, then you need to give an argument for why this is. Bohr and Heisenberg did not do so. No physicist has done so. No physicist can do so, because, at least not insofar as they're talking purely about physics. Because physical data, which one would have to make reference to in a physical argument, can only make sense through the filter of assumptions like that one. So the only way in which that assumption, the assumption that that mathematical description of unobserved particles existing in a joint superposition is a real thing, that it actually refers to the real state of those objects as they actually in fact are, the only way that one can justify that claim is through a philosophical argument. Now, a philosophical argument for this claim could work or it may not work. You may even be able to come up with a philosophical argument which is convincing. And I would like to see such an argument, because I've never seen one. I think that saying that objects, when they are unobserved, actually really do exist in a mathematical superposition is just a reification error. And I've never heard any argument to the contrary. So anyone who favors an idealistic interpretation of quantum mechanics, please give me an argument for this. I want to hear it. I've never heard it. No physicist that I'm aware of has ever even tried to do this. In fact, most physicists, probably even close to all physicists, I would even say, except maybe for some Bohmians, are probably unaware even of the need to provide such an argument. They think that because the mathematics says so, it must be real. But such an argument hasn't been given. And as I said, if you're going to give an argument for that proposition, please do not say that it is true that unobserved objects exist in that kind of statistically distributed joint superposition, because that's what the math says. The math itself doesn't say anything. It's false that that's what the math says. The math just provides a useful model within the context of certain framing assumptions. Okay, this would be like saying that the Earth is in the center of the solar system because that's what the mathematics of Ptolemaic astronomy says. Right? I mean, that wouldn't make sense at all. Ptolemaic astronomy is just a theoretical model which made certain assumptions, one of them being that the Earth is in the center of the solar system, which then grafted a mathematical apparatus on top of that assumption which was then able to explain observations. And the same thing is going on with quantum mechanics. There's a certain assumption, which is one of them being that prior to observation, objects exist in this statistical joint superposition. Grafted onto that is a certain mathematical apparatus, or rather I should say that the assumption emerges out of a reification of the mathematical apparatus, the mistaken assumption that the mathematical apparatus actually refers to something that exists in reality rather than just serving as a useful model for making predictions. And then it's just blithely assumed that this claim refers to something real. That's a whopper of an assumption. It is an absolute whopper of an assumption that unobserved particles exist in a joint superposition that is statistically distributed as described by Schrodinger's equation and the uncertainty principle and so forth. There's no reason for that. There's no reason to think that. So if anyone watching this believes that quantum mechanics proves idealism, I'd like you to give me an argument for this claim. That's the first assumption that Bohr and Heisenberg made. The other assumption is also a whopper. And that assumption is that if an object does not have definite ascertainable, does not have properties which are definitely ascertainable and measurable, that is, if the properties of an object are not such as can be precisely measured and determined, then that object doesn't have those properties and therefore doesn't exist. That's a whopper of an assumption. And it's a blatant foray into metaphysics. The only way to give an argument for that claim is to provide a philosophical argument for it. You can't do this with physics alone. That's very important to understand. I hope that's clear. And the final point that I want to make is that if you take those two assumptions and you conjoin them together, you get something that's rather shocking. So take the assumption number one says that when objects are not observed, they actually do exist in a joint mathematical superposition such that none of their quantum properties are precisely ascertainable. And assumption two says that if the quantum properties of some particle are not precisely ascertainable, then that particle doesn't exist. Now, if you conjoin those two assumptions, you get the proposition that a particle which is not being observed or measured does not exist. That's idealism. Okay? That is the central claim of idealism. That all of those things in reality, or what we take to be reality, which are not being consciously perceived or measured, if you like, by some mind, do not exist. That which is not perceived does not exist. That is idealism. Those two background assumptions, which frame the Copenhagen interpretation of quantum mechanics, when combined, entail idealism. And so what that means is that the Copenhagen interpretation of quantum mechanics doesn't prove idealism, it presupposes it. It presupposes idealism and then interprets the data of quantum mechanical experiments within that context, within that philosophical and metaphysical context. But commenters like Johann Ratz or Inspiring Philosophy or any of 1,000 other pseudo-mystics or pop science commentators have not been sufficiently attentive to things like philosophical premises and so on, and a lot of physicists have been complicit in this as well, that they have made the mistake of thinking that the interpretive framework for quantum mechanics is metaphysically neutral, and that when they examine its results and interpret it and provide theories for it, that all of that is metaphysically neutral, that it has no preset metaphysical commitments, and they think that these results, that these metaphysical conclusions, a metaphysical conclusion like idealism, just purely follows from the quantum mechanical results. No, the quantum mechanical results are interpreted within an idealistic framework because the two assumptions of the Copenhagen interpretation that I mentioned entail idealism. And they entail idealism without even having to go into a discussion of the physics. You take those two assumptions alone, and you get idealism already without even having to talk about physics, without even having to talk about the results of any experiment or of the results of any proof of any theorem within the quantum mechanical formalism, or anything like that. So what happens is that they reify a mathematical construct, grant it reality, make the metaphysical assumption that only that whose properties are precisely ascertainable exists, and then you already get idealism. And so it's no surprise that people who subscribe to the Copenhagen interpretation are pushed into saying things like that the conscious observer plays a fundamental role in the collapse of the wave function. All that conclusion is baked into the background assumptions of the Copenhagen interpretation, which are present before you even start doing experiments. So it's no surprise that that's arrived at. So what I would say is that quantum mechanics doesn't prove idealism, it presupposes it and interprets its results within that framework. And this is a mistake that everybody makes. You know, when I sat down thinking about making this video, I realized that a good alternative title for it could have been Why Physicists Are Really, 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 Really Bad at Philosophy. And I don't mean to pick on physicists here, they're fine people and all that, but as an empirical generalization, this tends to be true. I mean, if you don't believe me, just listen to Lawrence Krauss talk about nothing, or Neil deGrasse Tyson talk about God, or I mean, for God's, or Steven Weinberg, or just about any scientist that you'd care to name. Watch what he does when he enters into a discussion of philosophy. He makes elementary errors and really stupid errors. Physicists, as a rule, are not known for their philosophical acuity. They're just not. And so they will tend to make implicit background assumptions like those that Bohr and Heisenberg have made. And then other people, looking at their work, who are excessively awed by their mental prowess, swallow up everything that they say, including those metaphysical background assumptions, and they just grant the status of truth to them without thinking to examine them. And so they arrive at conclusions like quantum mechanics proves idealism. It doesn't. The Copenhagen interpretation presupposes idealism. That's the central point of this video. Now, I realize that I have been my traditional long-winded self here, but I wanted to be absolutely clear on this point. And really, I could just end the video here. But for those of you who are not inclined to parsing metaphysical arguments, and who would rather see a specific example of an alternative theory which makes equivalent predictions to that of standard quantum mechanics, but which does not have any of these idealistic consequences, let me give you an example. There is an interpretation of quantum mechanics known as de Broglie-Bohm pilot wave theory. And it is fully deterministic. It is just like Newtonian mechanics, but with one addition. And that is the addition of something called the quantum force. And essentially what it says is that particles do not exist in any kind of superposition when they're not being observed. No, they have a definite location. And by the way, another feature of Bohmian mechanics is that the only really relevant quantum property for a particle is its location. Spin is not considered a real property because of the fact that in order to measure spin, you have to orient the Stern-Gerlach machine that measures it in a certain way, and so that measurement will depend on the orientation. And therefore, a lot of Bohmians would probably conclude that spin isn't a real property of a particle. It's just something that's dependent on orientation. So the only real quantum mechanical property within Bohmian mechanics is position, and all other properties are reduced to position. But it says that when a particle is not being observed, it does have a definite position. This does not mean that we can always precisely ascertain it. In fact, we can't because of Heisenberg's principle. But nevertheless, it does have a definite position. And given that definite position, and the initial conditions under which that particle is subject, we can then trace out the influence upon the particle of the quantum force to determine, in a purely deterministic fashion, the location that the particle will have at the end of any given experiment. Now, because we are not able to precisely ascertain the initial conditions of the particle because of the uncertainty principle, we therefore will not also be able to precisely ascertain the end conditions, hence the necessity for statistics. But within Bohmian mechanics, there is explicit the presupposition that if, the claim that if the initial conditions of a particle could be precisely ascertained, the ending conditions of it could also be precisely ascertained. And so it's totally deterministic in that sense. Another difference from standard interpretations of quantum mechanics within Bohmian mechanics is that although, like in standard interpretations, Bohmian mechanics uses the Schrödinger equation to describe the behavior of particles, it introduces an additional equation derived from Schrödinger's equation called the guiding equation, which, as the name suggests, explains the trajectory of a particle as subject to this postulated quantum force. That is, it guides the behavior of the particle in a certain way. I'll provide links to videos in the description that describe this if what I'm saying isn't clear. So, how does Bohmian mechanics account for the results of the double slit experiment? Well, the reason that particles, when fired through those slits, behave like waves and produce a wave-like interference pattern on the sheet when there is no measurement apparatus present by the slits, but produce a particle-like pattern when there is a measuring apparatus present, has to do with the influence of the measurement apparatus and the quantum force that is exuded by that measurement apparatus, because the measurement apparatus itself is composed of particles which obey quantum laws. The quantum force exerted by the measurement apparatus upon the particles or upon the system being analyzed in the experiment alters the behavior of those particles. And so, without the apparatus, the guiding equation dictates that those particles will produce a wave-like interference pattern, but in the presence of a measurement apparatus, because the conditions and the manner of influence of the quantum force have changed, that equation then dictates a particle-like clump pattern. And so it fully accounts for the results without having to assume those two things that I pointed out, that particles actually do exist in a mathematical joint superposition, and that if it is not possible to precisely ascertain the quantum properties of a particle, then that particle doesn't exist. Bohmian mechanics doesn't make those assumptions, and is able to explain the results of the double slit experiment. The kochen-specker theorem is also explicitly not a problem for Bohmian mechanics. Because remember, as I said, the kochen-specker theorem asserts that the conjunction of value definiteness and non-contextuality contradicts the quantum mechanical formalism. And really, I mean, this is a mathematical proof. It's not the result of an experiment. Just a kind of pedantic point. Inspiring Philosophy, in one of his videos, briefly claimed that there was experimental confirmation of the kochen-specker theorem. That's a meaningless statement. He seems to not understand what a theorem is. A theorem is just a deduction from propositions within a formal system. An experiment can't confirm a theorem. It can maybe demonstrate it, but it can't confirm it. What confirms the theorem is the derivation within the formal system, and no experiment could conceivably contradict it, at least within the confines set by the formalism. I mean, what the quantum formalism is it's basically linear algebra with one slight change. Rather than having the dimensions of the vector space in which one works be some integer, the dimensionality is expressed with a real number. And unlike in most typical vector spaces, in most kind of typical vector space theory where you sort of learn linear algebra, rather than having the real numbers as being the field over which the vector space is defined, it's really the complex numbers. So your scalars are all complex, and the vector components are complex. And as I said, there's a real number of components rather than an integer of components. And this introduces certain mathematical complications, but because of the nature of physical reality, specifically because of the fact that all probabilities which presume to describe the way the real world functions must ultimately add up to 1, this doesn't actually have consequences for the formalism that make it any different from the standard theory of infinite dimensional vector spaces. Technically, just as a mathematical construction, this would look very different, and there would be all sorts of issues for mathematicians to worry about. But physicists don't have to deal with it. So the quantum formalism is basically just linear algebra. It's just, a vector space defined over a field, in this case the complex numbers, and then the 9 axioms of a vector space. So for those who don't know what the axioms are, a vector space is basically a mathematical set, a collection of objects called vectors, and another collection of objects called scalars, those scalars being members of a field. I'm not going to explain what a field is. You can look it up. It'll take too long. But basically the idea is that in this vector space among these vectors, and this field over which it's defined, there are 2 operations, addition and scalar multiplication, and they're expressed in the following way: that with respect to addition, a vector space is an abelian group. Again, look up what that means if you don't know. I'm not going to, because I'm just saying it this way as a shorthand because I don't want to take a long time on this. With respect to addition, vectors form an abelian group. With respect to scalar multiplication is commutative, and then and then there are the 2 kind of distributive laws where you can distribute a scalar over the sum of two vectors, or you can distribute a vector over the sum of 2 scalars. And then there are the multiplicative properties of scalar multiplication relating to 1 and 0. So any vector multiplied by 0 gives you the 0 vector. Any vector multiplied by the multiplicative identity within the field, or 1, gives you back that same vector. That's vector space theory. That's what the whole quantum formalism is expressed in. So what the kochen-specker theorem says is that if we were to give mathematical expression to the claim of value definiteness and non-contextuality, that contradicts the axioms of the formalism in a deep way. Well, this is not a problem for Bohmian mechanics, because Bohmian mechanics is explicitly non-contextual. Contextual. It rejects non-contextuality. It explicitly affirms value definiteness, but it rejects non-contextuality because it says that the presence of a measurement apparatus can exert a quantum force on a quantum system and thereby alter the behavior of that system to something that it would not have been in the absence of that apparatus. So So yes, there's no problem from the kochen-specker theorem. Bell's theorem doesn't pose a problem either, because Bell's theorem only rules out non-local local hidden variable theories, and Bohmian mechanics is a non-local hidden variable theory. No problem there. The delayed choice quantum eraser experiment isn't a problem either, because and again, this will be easier if you look at Inspiring Philosophy's video and pause it to look at his diagram. I'm just describing it verbally because I'm too lazy to do all the snazzy video stuff that you'd have to do to actually put that in front of you. But for those two detectors, in which it is D1 and D2 and D4, where the photon could have come either from slit A or slit B, and it's not possible to ascertain the path information. The reason that a wave pattern is produced when a photon interacts with those detectors and not the detectors D1 and D3, where it is possible to ascertain path information, is that when one actually examines the paths that the photon would have to follow to get either to D2 or D4, depending on whether the photon originally came out of slit A or slit B, it would have to follow different paths, and therefore would have a different series of interactions with objects along the way, and therefore different manners of exertion of the quantum force would impact it. And so different exertions of quantum force applied to two different particles starting off from two different initial positions could conceivably produce the same result. And similarly for the two detectors where path information is ascertainable. So Bohmian mechanics doesn't make the assumption that that prior to observation particles exist in a joint superposition, but it's able to account for all of the experimental results of the late choice quantum eraser experiment. And the final point is that with regard to the question of the von Neumann chain and wave function collapse, because Bohmian mechanics rejects the assumption that unobserved particles exist in a joint superposition of states, the problem of what collapses the wave function never arises for Bohmian mechanics in the first place. Nothing collapses the wave function. There's no need to collapse it. There's nothing to collapse. The particle always has a definite, precise location. There's no wave function to collapse. So the whole issue of what it is in the von Neumann chain that actually initiates the collapse mechanism doesn't emerge at all. The problem just evaporates. So Bohmian mechanics is a realistic interpretation of quantum theory, which does not lead to idealistic conclusions. And the reason that it does not lead to idealistic conclusions is that it does not make those initial philosophical background assumptions that were made by Bohr and Heisenberg when they formulated the Copenhagen interpretation. And so, to summarize, my point is as follows. Whenever someone claims that a scientific theory, just as such, has some metaphysical implication or philosophical implication or other, your bullshit detector should immediately go off, regardless of what the person claims that the implication is. Scientific theories, just as such, do not have philosophical implications. They only have philosophical presuppositions. It is always wrong to ask what the philosophical implications of such and such a scientific theory are. Rather, the question to be asked is, what are the philosophical presuppositions of such and such a theory? In the case of the Copenhagen interpretation of quantum mechanics, those two philosophical presuppositions, two of them anyway, are that one, that the mathematical description of unobserved particles as existing in some kind of state of joint superposition actually describes the real state of those particles when they're unobserved. That's assumption number one. And assumption number two is that when it is not possible to precisely ascertain the quantum properties of a particle in a quantum system, then that particle is said not to exist. And as I pointed out, the conjunction of those two assumptions already by itself entails idealism. So quantum mechanics itself, the results of its experiments and so on, have no role to play whatsoever in getting you to idealism. The initial background assumptions of the Copenhagen interpretation do that all by themselves. And if you formulate an interpretation of quantum theory with different philosophical background assumptions, you won't get idealism. So, if you have to decide between something like the Copenhagen interpretation or Bohmian mechanics or some other alternative theory, one must make that decision on the basis of metaphysics. One has to compare the metaphysical assumptions of the respective theories and then make the determination on the basis of philosophical arguments. So if you have philosophical objections to idealism, for example, you're going to go with something like Bohmian mechanics or some other realistic theory. It is always wrong to say that physics or science as such proves any particular metaphysical conclusion, because it is only within the context of certain metaphysical background assumptions that it is even possible to create a framework within which one can formulate scientific theories in the first place. So people like Inspiring Philosophy and Johann Ratz are just wrong. This is an elementary philosophical mistake that they're making. Quantum mechanics doesn't prove idealism, and physicists are really, really, really bad at philosophy. That's it. That's all I wanted to say. Thank you for listening.